Hello everyone. In this video I am going to show you how to find deflection using method of double integration. This method is suitable only for elastic deflections for which the beam slope is very small. The method considers only deflections due to bending. Positive values for slope are counterclockwise and positive displacement is upward. This is the sign convention which we use for this example. So this is our example. So it says determine the maximum deflection of the joist using method of double integration. EI is constant. So you can see a simply supported beam here, and span is given 10 meters and distributed load is given 4 kN per meters. So these are the common three type of supports, and first one is roll or rocker. Simply supported condition also apply the same theory. So it says delta equals 0. So this delta means the deflection. So at the support deflection is 0, but you can see theta here, it's the slope, but slope is not equal to 0. That means there is a slope in roll or rocker or simply supported condition. Second one is pin support. Here also delta equals 0, that means deflection is 0, and but there is a slope. Third one is fixed support. Here deflection is 0, slope also 0. So it's the fixed support condition. You can see 6 beams here, and it shows the how deflect these beams in different conditions. So A, you can see roll support and fixed support. So here the deflection shape of this beam under point load. Likewise you can see 6 examples. You can observe and study these conditions for your further knowledge. So this is our beam. This below diagram you can see deflected shape of the beam. So middle of the beam you can see I marked here as V, that is a deflection. Actually it's the maximum deflection. Okay, our first task is to find in support reactions. So for that, first I consider sum of all the vertical forces. So if I consider vertical forces, I have to write AY plus BY, which are these two support reactions, and 4 times 10, that is the this distributed load. 4 times 10 is the resultant force due to this distributed load. So if I simplify this, I can get AY plus BY equals 40. So if you closely look at this beam, you can see there is a symmetricity in this beam. Due to this symmetric nature, I can say AY is equals to BY. So finally I can write AY equals 20 Newton and BY equals 20 Newton. So actually it's kilonewton. And those are support reaction. AY equals 20 kilonewton and BY equals 20 kilonewton. Then I will consider part of this beam. So I will cut beam like this, and I will mark distance from A as X. So I will measure X from point A to point B. Okay, if I redraw this, so this is the beam and this is the support. So I can't deal with this distributed load, therefore I have to convert into resultant force. So this distance is X. So I have to mark resultant force here. So this is a distributed load and its magnitude is 4 kN per meter, and this distance is X. So I can write a resultant force as 4 times X. So it comes 4X. So this is the resultant force of this small part of the beam, and distance is middle of this beam. So this distance is X. Overall distance is X for this small part. So this part is X over 2 and this part also X over 2. So this resultant force is acted middle of this small part of the beam. I will redraw it in next page. I will show you clearly ground picture. Okay, you can see the small part of the beam which I showed you before. So here I am going to find M. So I am going to take equation for M, which is bending moment. So I will mark this bending moment as it gives a sagging moment for this small part of beam. If I give a moment for this direction, this beam bends like this, right? So it's sagging moment. That's why I mark this M to this direction. So in order to find bending moment, I'm going to take moment about let's say this point is P. I will take moment about point P and to the counterclockwise direction. If I take moment about point B, I will have M, which is this moment, and plus 4x, which is this force, and distance to this force is x over 2 minus 20x, which is this force. So moment due to this force is clockwise, we consider counterclockwise direction, therefore I put minus sign here, and 20 is the magnitude of the force and x is the distance to this force from point P. So if I simplify this, I can get answer for M as M equals 20x minus 2x to the power 2. Okay, now I will apply method of double integration. You have to memorize this important equation. So you can see here d to the power 2 v over d x to the power 2 equals m over ei. So you have to memorize this equation, and from this equation I will take answer for this m, which is moment. So if I solve this equation for m, I can write m equals ei times d to the power 2 times v over dx to the power 2. Then I will substitute this equation for this m. If I substitute this, I can write it like this. E is the material modulus of elasticity and I is the beam's moments of inertia computed about the neutral axis. Next I will write this equation here. Next I am going to integrate this equation. So I will mark this equation as first equation. So if I integrate this, I will have, if I integrate this part, I will have ei times dv over dx equals, if I integrate 20x, I have to write 10 times x to the power 2. If I integrate minus 2x squared, I will have to write minus 2x to the power 3 over 3 plus c1. Because this is indefinite integration, therefore I have to put a constant here, so I marked it as c1 and I will label this equation as equation 2. Next again I will integrate this equation 2. So if I integrate this, if I integrate this part, I have to write eiv, v is the deflection, and if I integrate 10 times x squared, I have to write 10 times x to the power 3 over 3. If I integrate this part, I have to write minus 2 times x to the power 4 over 12. If I integrate c1, I can write plus c1x plus c2. Here also I have to put a constant here because this is an indefinite integration, and I will label it as equation 3. So this is our beam and this is the deflected shape. I measure this x from point A to point B. Next I am going to apply boundary condition for these equations. So at A there is a simple supported condition and B also simple supported condition, and in simply supported conditions, deflections are 0. So at A, x equals 0, it is the starting point, and V equals 0, that is deflection equals 0. So I will apply this boundary condition to equation 3. I will substitute x equals 0 and V equals 0 into equation 3. So this is the equation 3. When I substitute it, this part becomes 0 because V equals 0, and these all three parts becomes 0 because there is x here and x equals 0, and finally only left is C2. So eventually C2 is equals to 0. Now we know one constant, right? Now we found one constant. So there is another constant of C1. So next we will see how we find C1 constant. Next I will apply boundary condition for B. So B, x equals 10. So this overall length is 10 or span is 10 meters. Therefore at B, x value is 10 and V equals 0. Here also deflection equals to 0. So substitute C2 equals 0, we found it before, and x equals 10 and V equals 0 into equation 3. So this is the equation 3. So I will substitute it, 0 as V and x equals 10. So if I substitute this, I will have 10 times 10 to the power 3 over 3 minus 10 to the power 4 over 12 plus C1 times 10 plus 0. So if I simplify this, I can get C1 equals minus 166.7. So now I successfully found C1 and C2. Now I can write equation 3 like this. So I can substitute values of C1 and C2 to this equation 3. Now I know this constant. So I label it as equation 4. Next I am going to apply another boundary condition at middle of the beams, which is x equals 5 meters, because this overall length is 10 meters. Middle of the beam is 5 meters. At middle of the beam, deflection reach its maximum value. So you can see this is a deflected shape. You can see here also this deflection reach maximum at the middle of the beam. So substitute x equals 5 to equation 4 in order to find the maximum deflection of the beam. So next I am going to do this. I will substitute x equals 5 to the equation 4. This is the equation 4. Next I am going to substitute x equals 5 to these x's in this equation 4. So if I substitute this, I can write EIV equals 10 times 5 to the power 3 over 3 minus 2 times 5 to the power 4 over 12 minus 166.7 times 5. So if I simplify this, I can get V max. So this is the maximum deflection. V max equals minus 521 over EI. If you are given values for E and I, you can substitute and get final answer. Since this example they are not given values for E and I, therefore I will write this like this. So I will keep it as it is. So it says minus 521 over EI. So according to our sign convention, it says positive displacement is upward. So its opposite meaning is negative displacement is downward. So in our case it's negative, that means displacement is downward. So it's obvious now, you can see this is downward displacement because load is acted on the beam. So this is our final answer. Vmax equals minus 521 over EI and its downward displacement.